A micrometeoroid the size of a grain of sand traveling at tens of kilometers per second does not behave like a slow puncture, it vaporizes on impact and transfers its energy impulsively. That is the core technical problem. Hypervelocity micrometeoroid and orbital debris, MMOD, impacts create tiny but catastrophic penetrations in flexible pressure garments, and the physics of gas escape and human physiology together set a very short deadline for any corrective action, on the order of tens of seconds to a minute, depending on hole size and circumstances. An extravehicular mobility unit is a layered, pressurized system. From the outside in the outermost layer is the thermal micrometeoroid garment, TMG, woven aluminized fabrics, Nextel and Kevlar layers, intended to blunt and fragment incoming particles. Beneath that are restraint and insulating layers and a gas-retaining bladder typically made of urethane-coated fabrics. The suit is normally pressurized with pure oxygen at roughly 4.3 psi, about 30 kilopascals, low compared with cabin pressure but high enough to maintain oxygen partial pressure for life support and to simplify suit mobility. When a micrometeoroid strikes, the sequence of physical events is rapid. The projectile undergoes shock compression and vaporization, plasma and molten ejecta are produced, fibers in the outer layers are severed, and spallation can drive secondary fragments into deeper layers. If the kinetic energy and local failure exceed what the layered architecture can absorb, the bladder is pierced and a conduit opens between suit interior and vacuum. Once a hole exists, gas dynamics determine how quickly the suit depressurizes. At the pressures and characteristic hole sizes involved, flow into vacuum is compressible and often choked. The flow velocity at the throat reaches the local speed of sound, making the mass flux dependent primarily on upstream pressure and throat area rather than downstream conditions. For choked flow, the instantaneous mass flow rate through the opening is proportional to the upstream pressure. Because the internal gas mass is itself proportional to pressure, ideal gas law, the pressure decays approximately exponentially with time. The exponential time constant is inversely proportional to the hole area and directly proportional to the suit internal volume and gas temperature. Practically, this means that a very small puncture, a fraction of a square millimeter, produces a slow leak measured in minutes, while a tear a few millimeters across can reduce pressure to dangerous levels in tens of seconds. Physiological constraints overlay the mechanical timeline. The suit provides a pure oxygen environment at reduced total pressure to maintain adequate oxygen partial pressure for tissues. A sudden drop in total pressure reduces the partial pressure of oxygen linearly. The human central nervous system is sensitive to hypoxia. With no oxygen replenishment, cognitive impairment and loss of consciousness occur within seconds to a minute depending on residual oxygen partial pressure. Separate from hypoxia is ebulism, the tendency of body fluids to boil when ambient pressure falls below the vapor pressure of water at body temperature, the Armstrong limit near 6.3 kilopascals. Human tolerance to exposure to vacuum without protective countermeasures is measured in tens of seconds for useful consciousness and survival without permanent injury. Therefore, the combined gas leakage and physiology produce an operational window often summarized as on the order of 60 seconds for larger breaches, enough time for an automated or manual valve to isolate a leak path, for a crew member to apply a patch, or for rapid rescue, but not enough time for elaborate procedures. Several important constraints and edge cases complicate this simple clock. First, hole geometry and secondary damage matter. A clean circular hole created by a pure penetrating particle is mechanically different from ragged tearing produced by a fragmenting impact. Ragged tears can grow under tension from pressurization and from movements, converting a tolerable leak into catastrophic failure. Second, particle energy scales nonlinearly with mass and velocity. Very small particles at extremely high speeds can produce plasma jets that ablate multiple layers rather than forming a simple hole. Third, internal suit geometry and the presence of clothing, tools, or structural elements near the impact site change local flow fields and can create localized pocketed depressurizations that injure tissue without causing a global pressure loss. Fourth, detection matters. A slow leak may be noticed via suit pressure telemetry and alarm systems, but a rapid tear might outpace sensor sampling rates or telemetry latency, leaving no practical warning before physiological impairment begins. The suit design itself is governed by trade-offs that set hard limits. Increasing micrometeoroid protection requires thicker, stiffer, or more layers, which reduce mobility and substantially increase mass. Enhanced outer layers can blunt hypervelocity particles but cannot guarantee complete containment of molten plasma. Adding redundant inner bladders increases survivability for small penetrations but adds complexity and points of failure. Active mitigation concepts, fast-closing valves, autonomous patch dispensers, inflatable internal bladders, or self-sealing polymers introduce mass, power consumption, and reliability concerns. Any active system must detect a breach, characterize its size and location, and respond in fractions of a minute without hindering normal operations. On the operational side, tethering, buddy systems, and proximity to a pressurizable airlock reduce consequences but do not eliminate the minute-scale urgency of a significant suit tear. There are also environmental uncertainties. Micrometeoroid and debris fluxes vary with orbital altitude and inclination and with sporadic events such as micrometeoroid streams. Predictive shielding requirements depend on probabilistic models that cannot guarantee zero risk. Simulating hypervelocity impacts in the laboratory reproduces many failure modes but cannot fully capture every angle, material aging state, or combined geometry effect that may occur on long missions. Moving forward, the unresolved engineering challenge is how to combine high-fidelity, ultra-fast detection with mechanical countermeasures that work within the strict mass, volume, and mobility budgets of a spacesuit. Materials research aims at self-healing bladders that reseal under vacuum, nanoporous sacrificial layers that vaporize benignly without transmitting shrapnel, and distributed sensor skins that localize breaches in milliseconds. Systems research is exploring ultra-fast closure valves and internal microactuators that can isolate damaged suit segments without cutting off life support, but those systems must be demonstrably reliable over years in a radiation and debris environment. The open technical question is whether a suit can be engineered to detect and neutralize a hypervelocity puncture of centimeter-scale severity in less than the physiological threshold for irreversible harm, while keeping mass and stiffness compatible with human mobility on long-duration missions.